Welcome back to our statistics learning session. In last session, we worked on this slide on Wall's test and we tried to define what a Wall test is, the equation of the Wall's test, where n tends to chi-square, where n tends to be a chi-square distribution. This is what we proved last time. Chi-square are the distribution. Now, making progress on that, what we'll do is we'll have to create something, a test statistics, and this will be our test statistic. This will be our test statistic here. And what should be greater than? That's the question. It should be greater than q alpha. It should be greater than something, right? It should be greater than q alpha of chi-square distribution. That should be greater than. And if that's the case, then test status has a greater than q alpha of chi-square distribution. And how do we find out the q alpha of chi-square distribution? How do we do that? Q alpha of chi-square distribution. How do we do that? We can, with d degree of freedom, we can do that by going to a chi-square table and finding out the value of the chi-square, q alpha of that value. Now, one thing I want to focus your attention is this remark, where Wall's test is also valid if H1 has a form theta greater than theta naught, or theta greater smaller than theta naught, or theta is equal to some other value than theta naught. Why is this? This is because when we define Wall's test, Wall's test had what Wall's test had? Can you tell me? The hypothesis of Wall's test. The hypothesis of Wall's test was is the third version. Theta mle h naught was equal to theta naught, and alternate hypothesis was theta mle was not equal to theta naught. It was everything except theta naught. That's what we were proving. Now this is everything except theta naught. That's what we are proving. That's the alternate hypothesis. Now look at this. Theta is smaller than theta naught is a subset of this. Theta mle theta not equal to theta naught. This is a subset of that. And this is also a subset of this. Correct? This is a subset. And this is a subset. And theta equal to theta naught. This is a subset of that, because theta 1 can be any value from any value beside theta naught. So this is a subset of this. So these alternate hypotheses are more relaxed than our alternate hypothesis of Wall's test. Therefore, they are all plausible alternate hypotheses of the Wall test. They are all alternate hypotheses. They are all plausible. That's what I'm trying to say here. And Wall hypothesis is by design a stricter hypothesis. Because Wall hypothesis is usually focused on multivariate Gaussian. Now the question arises: what happens if there is only one variable, or there's only one variable, single variable Gaussian? What happens then? In this case, what we can do is we can try to prove ourselves what would happen, and that will help us to get a deeper understanding of the process. The thing is that we know that there's something called z-score, Now let's start with the our third version and modify it for a single variate Gaussian. And how does that work? We can do that by looking at this one where we have go here. We have something like this. We have something like this where we have something like this where we have square root of n mle minus theta is in a infinity becomes something like a zero square distribution. It's a normal distribution. Now what happens if we do this? What happens if we take the instead of a normal distribution? What happens in the standard distribution? What happens then? We can just divide this by standard deviation, which brings us to the theta mle minus theta, and it becomes n for a standard normal distribution. And now, what would be the test of this? Test of this would be something like this: delta n square root of n theta mle minus theta would greater than some q alpha and of some normal, standard normal. Okay, this would be the test. Now let's look at some other thing here. What if we square this? Now let's begin with this again and square this on both sides to get a chi-square distribution. To get a chi-square distribution, let's take this normal here, the standard normal here, and square on both sides. And let's square this on both sides. What would happen here? Let's square this on both sides and theta mle minus theta and square this and square this on both sides. If we do this, this should be happen. This should come something like a. Um, this should give us something like square theta mle theta. And what will be test of this? This should be a, something like tends to become a um, tends to become a uh, chi-square distribution with a single variable because there's only one variable. It's going to be a chi-square distribution. Now, what will be test of this? The test of this would be something like this. Um, chi-square, um, chi-square. If we divide by this and theta mle and square, and it will test greater than something of a q alpha of chi-square 1 with a single degree of freedom. And what if we do square root of this? If we do square root of this, then it will become something like this, which is very similar to what we have derived before. Theta mle minus theta would be greater than square root of q alpha q1 square. Now look at here. This statement is very similar to this statement. Therefore, what we can convince ourselves is that n1 is very similar to chi q alpha uh, q alpha 1 q alpha of chi square distribution. They are very similar. We also can say that Instead of doing Q alpha, we can say that we can further go and say that it's not only Q alpha, it should be Q alpha of N01. We can say this too. And if you do this, then Q alpha of normal distribution, standard normal distribution is very similar to Q alpha chi1 square distribution. And therefore we can convince ourselves that when it is a single Gaussian, we don't need to go to chi-square. We can just use a z-score test to do that. And then let me quickly summarize what we learned today. We learned about Walsh test and creating a test statistic of Walsh test, and not only test statistics but also test out of test statistics. And after that, we talked about why Walsh test is very conservative and how we can accommodate other lesser stricter form of the alternative hypothesis such as delta, not only delta but theta is greater than theta naught, theta is smaller than theta naught, theta is equal to something other than theta naught. How we can accommodate those tests, and what happens if the Walsh test, if we are only looking at a one single dimension instead of multivariate Gaussian, is a single variant Gaussian, what happens then? Then the test becomes more like a Z test. So that's all for today. I'll see you next learning session. Thank you so much.